Dear students, in last few videos we studied vectors, vector spaces and linear mappings at general but abstract level. In this chapter we will add some intuition and geometric interpretation to various concepts that we learned. How we should account for distances, how we should account for angles. Now you might have learned all these things in your earlier classes or in other courses, but we will study them in a way that we can use some of the terminologies consistently with the machine learning literature. Now for this module, the kind of mind map we are going to have is that we will start with the inner product. From inner product, we will try to understand how it induces norms, how these norms are used in orthogonal projections, and these orthogonal projections ultimately form the backbone of singular value decomposition, K rank approximation, as well as principal component analysis. Moreover, whenever we are talking about projections, we have to account for the angles that exist between various vectors, and also we have to measure the length of projections and how much loss we are incurring when we are projecting one vector into a lower dimensional space. Now with that, we will go forward and quickly get started. So we will try to understand what these words mean, and we will start with something called as norms, and norms make frequent appearance in machine learning literature. So let us define norm on a vector space V as a function that maps any vector V to a real number. Now, when we talk about this mapping, we denote this mapping by this what we call as double modulus defined on V, resulting in a real number, such that you give a vector x and you apply a transformation, that output should be one real number. And for any transformation, this is also type of transformation, to classify as a norm, it should meet three conditions. So first one is, let us say there are two vectors, x vector and y vector. We can always add two vectors as long as their dimensions are consistent. We can take their norm. Their norm, when added together, should be less than sum of their individual norms. This is also known as the triangle inequality. If you remember that if there are two sides A and B, and third side is C, then length of C should be less than A plus B. And from here we can see that norms can also be used to measure certain distances, and we will use that particular result very powerfully in various aspects of machine learning. Now, second thing that these norms must follow is that they should be positive, definite. And we will also talk about positive definiteness in the context of matrices and the power they give to us when we go to spectral theorem and such. So positive definite says that if we have a vector x and we take its norm, it should be always greater than 0. And when this norm of x is equal to 0, this implies this vector x has to be equal to 0. And example here could be, let us say that length of a vector is qualifies to be a norm. Then we say that if this particular vector has its end point at 2 comma 3, and if we measure a distance as 3 minus 0 plus 2 minus 0 and its square root, we would always see, as long as we are in real space, this number is always greater than equal to 0, and this would be equal to 0 if and only if this tip coincides with the origin, or 0 comma 0. In that case, length would be equal to 0. And we call this length that we typically measure using this Euclidean distance formula as Euclidean norm. So this is, I would say, a fancy name for a thing that we keep on consistently using throughout in mathematics. And third thing that we should have with norms is that if we multiply a vector with a constant in a real space, then we can write this as modulus of that constant multiplied by that norm. Now these two results, that this is positive definite and a vector multiplied by constant, they are also interrelated if you see carefully. That means this norm has to be always positive, and to ensure that if lambda is negative, even in that case the result is positive, we make sure that the modulus of lambda or that particular constant is taken. Now the two specific examples that we keep on using in terms of norms, first one is the Manhattan norm, what we also call as Manhattan distance. So if we are given a vector x and it has various entries x1, x2, x3 and so on, I'm writing this in a row form just for convenience, and we define Manhattan norm as norm of x1 equal to x1 modulus plus x2 modulus plus x3 modulus all the way till xn and so on. So basically what we are doing, we are taking out each element, taking its modulus and summing it with our other elements, and in compact form we can write it as I to 1, I from 1 to n and modulus of xi. And this particular norm is also typically used when we talk about lasso and ridge regressions. The second norm that we have already talked about is Euclidean norm, and it is defined as norm of order 2, which we also write as take each element and its square and then sum it, I equal to 1 to n, and it take the power as we are raising it. So if we are raising it to 2, we are taking the square root. Now this xi square is also the product xtx and its square root, because if you take one vector, take its transpose, multiply it by the vector in its original form, and you're basically taking square of each element and adding them together. Now the way we have defined a Euclidean norm, we can define any norm of nth order. So I can write this xn as something raised to power n summation I from 1 to n xi raised to power n. So you can define third norm, fourth norm or nth norm as we define the first two order norms. However, in machine learning, the Manhattan norm and Euclidean norm are most commonly used, and even out of these two, unless specified otherwise, we would always be talking about n equal to 2 whenever we are introducing the word norm without qualifier. Now this norm brings us to something called as the inner product or dot product. Now if you recall, in last uh, discussion we mentioned xtx, and this xtx and its square root classifies to be one single number, so we are satisfying the condition of a norm. And this is also dot product. So if we are given a vector transpose x1 x2 x3 and we multiply it with a vector or original vector without transpose, we can simply write this as x1 square plus x2 square plus x3 square, and hence this becomes the dot product that multiply the corresponding elements and add them together. So we can define the inner product on two different vectors, and we say that if we are talking about specific dot product, we can write x transpose y as summation I from 1 to n xi yi. However, this dot product is one of the inner products. In today's lecture, we will take more of a generic view that what is the difference between the dot product and inner product, and what are the other kind of inner products that may exist. Now, if you recall, In our previous sections, we talked about linear transformations, and we were defining linear transformations, that let us say that phi is a linear transformation on x such that the output becomes ax if we multiply it by some matrix A. We can define bilinear transformations in a similar manner. That is, let us say that there are two vectors x and y, and we define some linear transformation on both x and y. Then we can write this as x and y are getting transformed, and this is the typical notation that we writing them in the this kind of bracket. Now the good thing about these bilinear transformation is that they will individually follow the properties of linear transformation. For example, our x is coming from lambda x plus sigma y, and our y is now replaced by z. Now, if we have to expand this, we can safely write it as we would do in case of simple linear transformations, that lambda can come out and we can define this transformation on x and z separately, plus our psi would come out, and we will again define this transformation and y and z separately. And when we talk about this transformation, as long as it is by abiding the properties of linearity, that means multiplying by constant is allowed or adding two vectors of same size is allowed, we would say that this transformation satisfies the property of being classified as the bilinear transformation. Now if we look at some transformation x and z, we can always define this transformation to be the dot product, and hence xz when operated by a dot product, we can safely write them as x transform z, and this qualifies to be a bilinear transformation. Hence we can say that dot product is a specific case of a bilinear transformation.
Now an important question arises. Would all bilinear mappings would qualify to be called as inner product? So the answer is no, because one of the most important conditions that would make any bilinear mapping to be qualified as inner dot product is symmetric, positive definiteness. And let us try to look into that what this means in the context of inner product. Now we learned that if we have two vectors, vector x and vector y, we can represent their inner product by this particular notation. And if we know that x is expressed with respect to some basis, y is expressed with some respect to some basis, and the coordinates of x with respect to basis b are represented by alphas, and coordinates of y with respect to same basis, they are represented by some betas. So what we can do, we can write x as, if it is in n, it is having a dimension of n, as I equal to 1, I from 1 to n, alpha I bi. We have learned this, that if we know any basis, then the coefficients of those bases would represent the coordinates, and that's what we are saying, that x vector can be represented in any other coordinate. Similarly, y can be written as j equal to 1 to n, beta j and bj. So now applying this understanding that we got for bilinear mapping, that we can treat this bilinear mapping as linear mapping in pieces. That would mean we can get these constants together, and we say that this can be summed from j1 to n, I equal to 1 to n, or vice versa, because the result would be symmetric. And hence we can get these alpha i's together, bi, bj, which are the column vectors representing the basis, and beta j, which represents the coefficients of y. And now we see that since this is the coefficient of x, these are the coefficient of y, we can write this as in compact form, that this represent the vector their transpose representing the x coordinate with respect to basis b. This is some matrix representation together which represents the uniqueness of dot product, and this is representation of y, and I am representing the non-standard basis representation using hat. Now this unique thing here is that the uniqueness of A would control that whether our bilinear mapping qualifies to be inner product or not. Now we learned that for any bilinear mapping to be qualified as an inner product, it needs to be positive definite, as was in the case of norm. And when we say positive definite, that would mean that if we apply some transformation on x and x, it should always be greater than 0 for all x belonging to a particular vector field, but they can not be equal to 0, because if x is equal to 0, our bilinear mapping should also be equal to 0. As long as these two conditions are satisfied, we would say that our matrix under consideration, or our bilinear transformation under consideration, is positive definite. Now let us also talk about symmetry. When I said that summation can be from ij or ji, that would mean that all the elements of aij and aji, they are same, representing the symmetry. And as long as these two conditions are met, we can say that our matrix under consideration is symmetric positive definiteness. Now let us again go back to the dot product. Now when we go back to dot product, we write dot product as x transpose y, and in that case, if we expand it using a, we can write this as x transpose ay, and a in that case is 1 0 0 1. And if we multiply any vector of dimension 2 cross 1 and take its transpose, it becomes 1 cross 2, making sure that it is size compatible with a. Y is of dimension 2 cross 1, we would end up with simple product x transpose y, and hence we can say that uniqueness of dot product is guided by 1001 in this case, which also happens to be the basis of R2. And this is a new interpretation of dot product that is typically used in machine learning, that we are doing nothing special. We are taking two vectors and introducing a symmetric positive definite matrix. And when we say symmetric positive definite matrix, that would mean that x transpose ax is always greater than 0 for all x belonging to some vector space, but that x cannot be equal to 0, because if that becomes equal to 0, then x transpose ax is equal to 0. However, the extension of this definition exists. We can also define symmetric positive or symmetric positive semi definite matrices, and that would mean that x transpose ax can be greater than or equal to 0 for all x belonging to certain vector field, but x is not equal to 0. That would mean even certain non-zero x can make this quantity equal to 0, and in that case we will say that it is symmetric positive semi-definite. Now this also makes a lot of sense. If we replace this a by uh, an identity matrix, then simply we are writing this as x transpose x greater than 0 if we are talking about real valued space. And if you look this closely, this is nothing but this is the square of various terms taken from 1 to n, xi, xj equal, and this has to be greater than 0 because we are talking about squares, because we also learned that this is something we calculate while calculating the Euclidean norm. So Euclidean norm is the square root of x transpose x, and hence Euclidean norm is also a derivative of a inner product or dot product. And needless to say that these dot products are immensely useful whenever we have to talk about the distances between the metrics. Now, before we go to the distances, let us quickly define how we would measure length of a vector. So we would say that in so if we are interested to calculate length of a vector x, we can always define it in terms of norm and especially L2 norm, and would simply say that it is x transpose x. Also, we learned that if we have two vectors x and y, we can take their inner product, and that is specifically represented by dot product as x transpose y, and this gives us a way to define or look into what we call as Cauchy-Schwarz inequality. Similar to the triangular inequality, we can state that if we take two vectors x and y, take their inner product and its modulus, it has to be less than equal to the norms that we define individually on x and y. And this gives us an interesting point that how we can define the angles between the two vectors x and y. So we can always write this, we can, when we remove this mode, we can write this as xy dot product has to be less than equal to xy, and since this mod is gone, we will introduce one negative sign and say that this has to be less than equal to mod x mod y, oh sorry, greater than equal to, so xy is greater than equal to negative of xy and their individual norms, and on the right hand side it has to be less than equal to x and y and their individual norms. So we can easily write this as -1 has to be less than equal to xy divided by mode of x, or sorry, norm of x and norm of y, and it has to be this middle term has to be less than equal to 1, because we will bring everything to the denominator, and this becomes cosine of angle between x and y, and this is also typically used to measure the normalized inner product. So we take the inner product of x and y and we normalize it with the norm of x and norm of y, whatever is the resultant quantity, that becomes the cosine of angle, or this, which we will use when we take the projections of one vector onto another. Now with this concept, let us introduce the term which we call as orthogonality. We are slowly and steadily getting towards all the ingredients required for singular value decomposition, where we will ensure this condition of orthogonality and orthonormality. Now, as we have learned that we can measure both angles and lengths using some measure of inner products, which in this case we are using as a dot product. And when we say that the cosine of angle between two vectors is equal to 0, we would simply say that two vectors x and y, they are orthogonal. And if we make the L2 norm or L1 norm, so we are sticking by default to L2 norm. If we can make norm of x equal to 1 and norm of y equal to 1, then we can say that these two vectors, if they meet the condition of orthogonality, they are orthonormal. So being orthonormal is the special case of orthogonal. And if these orthonormal normal vectors also constitute the basis, for example 1 0 0 1, you see that their dot product is equal to 0 plus 0, which is 0. Their angle is definitely equal to 90 degrees, because uh, cos of w is equal to 0, and hence we say that these two bases, which are typical Cartesian coordinates, they classify to be called as orthonormal bases or ONB. Now with this particular background, we are good to go to learn about orthogonal projections, which would be the topic of our next video.